Okay, my friends, so let's kick off this second day by kind of looking backwards while looking forwards as well. I want to talk about some of the terminology I used yesterday in the videos, but also kind of connect it to where we're headed next. So the course is called Probability and Statistics. I figure let's just start with probability because that's the first word in the title of the course. So if you've had me in courses before Math 243, we've established the definition of probability. At its most basic, it's just the rate at which an event happens. I've underlined event there because event has a probabilistic phrase that I want to get into, and we don't have to get into it right now. We can get into it later. I want to get you used to hearing the word in context versus memorizing a definition right now. And an experiment that contains possible events or outcomes could be as simple as flipping a coin, like we did yesterday. It might be as slightly more interesting as buying baby chicks at a store. For years, my family kept a small flock of backyard chickens. Turns out that every once in a while, when you buy a baby chick, when you're hoping to get a chicken, you might actually get a rooster. So what's the chance? What's the rate? What's the probability when you buy a baby chick that you get a rooster instead of a chicken? Or it could be as convoluted as something like this. Just recently, I found this cell phone on a bike ride home laying in a snowbank. Somebody, I guess, put it on their car and drove away and then lost it. What's the chance I'm able to get that phone back to its rightful owner? So you can see all of these are chances, but some are a little more straightforward than others. Let's start with the one that we actually did yesterday in the second video, I believe it was. That was when we flipped the coin, or I flipped the coin, I guess, 10 times, okay? And I was having a great time because if you remember from that last set of videos, I actually ended up getting 8 heads out of the 10 flips. So what's interesting about that, and we're going to do this later in the course, the experiment was take a coin and flip it 10 times. I knew I was going to flip that coin 10 times and just keep track of what happened. That was the experiment. The event that was so interesting was the fact that I got 8 heads out of the 10. And maybe as I was flipping that, you were kind of thinking, this is kind of strange. I'm getting lots of heads. Well, here's what the likelihoods of certain numbers of heads out of 10 flips looks like. Now, this right here is called a distribution of all the events of the experiment of flipping a fair coin 10 times. Take a peek at it. Notice up top, you could get 0 heads out of 10. You could get 1 head out of 10, 2 heads out of 10, 3, all the way down. Every possible number of heads you could get is listed there from 0 through 10. And then corresponding to that in the right column are the chances of that number of heads happening. Now, probably not surprisingly, 5 heads out of 10 is the most likely outcome. It happens about 24.6% of the time. So the event of getting 5 heads out of 10 happens about a quarter of the time. Now that number might surprise you a little bit. Why? Only a quarter of the time? I thought coins were 50-50. Well, absolutely true, but there's so many different outcomes from 0 through 10, and they have to be spread out in such a way that the likelihoods are all accounted for, that you end up with only 25% for 5. Look at the 4 and 6 head outcomes, about 20% each. Sometimes when you look at this, it might be a little bit kind of too hard to visualize in a distribution or a purely distribution form. So very often we'll also represent it graphically. This thing right here is called a histogram. Sometimes it's called a bar chart. I guess it really depends on who you're talking to and what the context is. We'll talk about both of those things as we go through this course. This is the exact same data. You've got all the different outcomes of the experiment down here, and you've got all the probabilities of those outcomes up here. Those of you that have taken psychology courses before might recognize the shape of this curve. This is called a bell curve or a normal distribution or a Gaussian distribution, depending on who you've talked to and which class you're in. But what's cool about it is it's simply, as I said before, a pictorial representation of the data in that distribution at left. Now you can see why I kind of reacted the way I did when I flipped 8 heads out of 10 flips. That should only happen about 4.4% of the time. So why did I react the way I did? because 4.4% is one of the smaller probabilities up there. That means it's one of the rarer events up there. That means it's getting close to being what's called a statistical outlier. And we'll go into way more detail about outliers later on. Now, this one's fairly predictable because we know that the coins were fair, so we can establish this right here. But what about the case of a baby chick? All right, you buy a baby chick. If you think about it, it's very much like flipping a coin. You buy a baby chick, bring it home, and it grows up. It's either going to grow up to be a chicken or a rooster. So what's the chance that you're going to get a rooster? Can you just say it's 50-50? No, you can't, based on our discussions from yesterday. Well, as it turns out, without getting too far ahead of ourselves, if you buy 10 baby chicks, this is what actually happens. These are the chances of getting a certain number of roosters out of 10 baby chicks. Now you can see this chart looks exceptionally similar to the chart back here. You've got the same number of outcomes on the horizontal, 0 through 10, and you've got the probabilities somewhere between 0 and 100% on the vertical. But we call this one skewed because it's kind of leaning to one side. This tells us something very important. It tells us that the chance of getting a rooster is not 50%. It's much less than 50%. And we're going to come back to this number, but I've been told by folks at the stores we've gotten these chicks from in the past that it's only about 10%. And we'll come back to that, how they establish that later on. Now, some of you might be looking down here at the 7, 8, 9, and 10 columns and going, wait a minute, 0%? There, you can't have a 0% chance of getting that number. And you're absolutely correct. All it was is it's rounding. It's rounding off. Those are the actual chances. However, if you knew the probability of a rooster was 10%, you could actually get these probabilities pretty straightforwardly. But here's the kick. How do they know that the probability of a rooster is only 10%? And while you're thinking about that, how do we establish the probability of being able to return a cell phone to its rightful owner? Well, let's chat about that experiment. Now, this one is definitely different than all the rest we've talked about so far. There are two outcomes. Either I get it back to the rightful owner or I don't. Now, I want you to just take a trip down memory lane with me right here. The phone you see in this picture, I actually did get this back to its rightful owner. It was pretty straightforward, actually. The kid that dropped it did not have a lock screen on his phone, so I was able to slide the screen open, even though the screen was completely smashed up. Went into his text messages and found one that said, hey, you coming home for dinner? Hey, everything okay? Oh, my goodness, I hope you're okay. And then I just called that number and I said, hey, I found this person's phone that you're trying to get home to dinner. And then the kid came and picked it up and it was fine. Now, as it turns out, the stretch of road that I found this on, I've actually found 2 other phones on this stretch of road. It seems to be a favorite for people dropping phones out of their cars. And all 3 of the phones right there, I was actually able to get back to their owners. But those aren't the only phones that I find and try to return. Years ago, my buddy Amy dropped hers on a climb we did of Mount Thielsen down in the Oregon Cascades. Believe it or not, I was able to backtrack and find her phone. So of those 4 phones I've told you about, I was able to get all 4 of them back to their rightful owners. As a matter of fact, there's only one that I've found that I haven't been able to get back. Take a look at this. This is Broken Top. This is actually a picture of the Green Lakes area. Broken Top's in the background there. See that big scree field right there? The best way that I've found to get off that mountain once you climbed it is to run straight down that scree field. Here's a picture of our son Max running down that scree field after a successful summit of Broken Top. Right after I took this picture of him, I put my phone back in my pocket and I looked down, and believe it or not, there was another cell phone on that scree field between my feet. I managed to run down a huge scree field and stop on top of another cell phone that somebody else had dropped. And believe it or not, the screen was in way better shape than the one you're seeing right here. That phone I have not been able to get back to the person. So I've got a 4 out of 5 record, which if you want to maybe abuse the idea of percentages would mean that I've got an 80% return rate. That's not exactly fair because we've only had 4 phones returned out of 5 total phones that I found. But the question is, how do you establish? What is the likelihood of getting a phone like this back to its rightful owner? Or falling down in the shower and breaking an arm? Or getting a flat tire on your way home from work? Or passing a class with at least a C? All of these things have probabilities. In a lot of ways, they're all binomial. You either do or you don't. You either get a flat or you don't. You either pass with a C or better or you don't. But how do you actually establish these probabilities? Let's talk about that more in the next video.